Very good morning to everybody. Welcome to the last session of first unit, Classical Mechanics. In continuation with the last session on the applications of Lagrangian equations for constrained motion, we will continue one more applications. So let's recap of Lagrangian equations. You know that the Lagrangian equation of a motion is given by d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to Qi, which is a general form of Lagrangian equation. For a conservative force, Qi is equal to 0. Then the Lagrangian equation of a motion reduces to d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to 0. The learning objectives of the present session is to understand the application of Lagrangian equation. The outcome of this session is to solve Lagrangian equation of a motion for constrained motion. Atwoods mission. Two bodies of mass m1, m2 is connected with an inextensible string passing over on a small pulley. This system is known as Atwoods machine. Atwoods machine is an example for conservative system with holonomic constraints. Let x be the vertical height of mass m1 with respect to pulley. So does m2 vertical distance will be L minus x. Let x be the independent coordinate. Then velocity of mass m1 is given by v1 is equal to x dot. Whereas velocity of mass m2 on differentiating L minus x, it reduces to minus x dot. Then the total kinetic energy of the system is given by T is equal to half into m1 plus m2 into x dot square. Then the potential energy V with respect to the pulley is given by V is equal to minus m1gx minus m2g into L minus x. We know that the Lagrangian is given by T minus V. Then the Lagrangian is equal to half into m1 plus m2 x dot square plus m1gx plus m2g into L minus x. Differentiating L with respect to x dot gives you m1 plus m2 into x dot, and differentiating L with respect to x reduces to m1 minus m2 into g. Substituting dou L by dou x dot and dou L by dou x in Lagrangian equation and differentiating d by dt with respect to dou L by dou x dot, it reduces to m1 plus m2 x dot double dot minus m1 minus m2 into g is equal to 0. Then x double dot on simplification reduces to m1 minus m2 into g divided by m1 plus m2 which is a required equation of motion for Atwoods motion. If m1 mass is greater than m2, then m1 descends with constant acceleration. Whereas if m1 mass is less than m2, then m2 ascends with constant acceleration. Please note that the tension in the rope and the force of constant is not seen anywhere in the Lagrangian equation. So far, in the first unit, we have covered how classical mechanics is developed from Newtonian mechanics to quantum mechanics. And we have seen how Newton's second law of equation is reformulated by Lagrangian using generalized coordinate system. And also we have seen the applications of Lagrangian equations for a constrained motion. Hope you enjoyed that. Thank you all.